Yeah, welcome back, guys. It's been a while, it's been a long time, I guess. I just created a new stream for this. And if you haven't already watched me stream, I was writing an entire blog post about getting into kernel development from the basics, like just from the bits to the top. So I have already finished like 3, 6, 9, and it's like almost 10 versions. I didn't actually stream those because I didn't have the time to do so. But this time I've decided to stream it. So let's see, where did we leave off last time? If we go here, so we were doing some debugging, more debugging, and I guess we tested how exactly we can jump right after we do MMU enable bit, because the next instruction after we turn on MMU would be invalid because there won't be any pages and we don't want those pages to be alive. So we temporarily create identity map and then we remove them. That's how it works. And I guess that's how I mentioned it too. Now we can think about the next step. Now we have MMU enabled. Okay, let's just see our code so we can get a little bit better understanding of what the fuck is happening. So now, okay, now let's see. We are here. We have a start that is good enough. We just setting things, and we also zero out our BSS, and we set up the vector table. We enable MMU, and then we jump into our virtual address, because these are the instructions that allow us to get into the virtual address that we have pages that are mapped to the physical address, and we don't want our kernel to access the physical directly. So we wanted to be indexing things within this VA, and it should work just fine. And we have the final kernel main jump. Okay, so we have a k main that's just going to init the uart and type to uart print messages and gonna just stop. And this is how our MMU looks like. And that was one hell of a battle. If you read my blogs, you know what exactly happened there. But then it's right now it feels me better. I believe I have a better grasp of what the fuck is going on there, because as you can see, we just have to have 3 physical base addresses, and then we should make sure we set the proper descriptors, whether it's a table descriptor or whether it's a block descriptor, and then also make sure that what sort of VA bits you are working with. Is it a 42-bit, is it 38-bit? Based on that, you need to make sure that your entry point is in the 3rd level or is it 2nd level, and you need to make sure you add your values in the respective level, and it should fucking work. And it did work for me, so I believe it's good to go. We can keep this aside and move on to the next thing. So we have a we have a kernel main that is working. We have MMU enabled. Now we need to think about how we can allocate more memory, because we have MMU and we have only like a certain amount of pages allocated here. So okay, because here if you see I have allocated everything from 8 something to physical base address this. So, and I also have allocated UARTs 9000 something into, no, 8420 into 8240 into 9000, which will be the UARTs memory map location. So what in case we want to, because our or whatever was that whatever process or whatever thing that is live might need to it might want to use extra space, extra memory. So it will definitely want to allocate more memory. So what exactly can we do that? So we need a helper function that could be like malloc that you might have seen in user space. Say calloc or malloc. Calloc is for kernel level, malloc is for user space. So we need to write a helper first of all in kernel level itself. So this helper is just gonna uh, allocate certain space, and it's going to give us a pointer back. That's it. Internally, all it has to do is what it exactly it has to do. It has to check for a space, empty space, and then it has to map those. What is that? Map those space tables with those entries. And we are in EL1, so I believe it should be possible. Now let's just get some little fucking whatever. I have a simple start dot s that inits MMU jumps into kernel VA and then jumps into kmain, all walking. Now we need to make a helper that can allocate memory. I guess maybe in kernel heap region. I don't know how exactly does this structure work. If kernel wants to allocate something, it might fall under kernel heap. But what if user space wants to allocate something? Where will it? No. So let's just say that it's going to be a generalized helper. So it's going to just allocate memory by creating page table entries. How does this actually work in Linux? Explain that first. case the user wants to allocate some memory, using malloc, where do this fall under, and who creates the extra page table entries, etc. Give me the bigger picture of how things works, and then let's talk about how we can create that in our helper. Okay. Okay, so we got bring up the MMU, enter the kernel virtual address space. You want to understand. So what's locating really means? So we have user code that's just going to do malloc, and internally it's going to go call a map and block. I know that because I guess it's like moving down some way. Grows and shrinks the heap and reserves additional virtual space region. Okay. When a process accesses an unmapped field, allocates. Okay, so kernel does allocate it. We're using alloc page. Okay, fine. Fills the new page table entry. I didn't understand shit, but I guess I got one thing out of it. That's that kernel has this helper. We can just search for it and see what the fuck it is. Okay, help physical page in the kernel equivalent to pointer to a struct page. Representing the allocated page or null. Okay. So alloc page will be the helper that will be used by the high level allocators. So basically at the lowest level, what does it mean to get more memory is just having page table entries for new VA. Am I right? I think so, because in general you are inside a virtual space, and let's say you try to access something and you get a page fault, so that memory is not in your hold, so you want that memory and you try to say that you want extra memory, and we get the page tables for it. That's it. I think that's exactly how I knew. I'm very fucking close. means two different things. Is physical frame using a bitmap or body allocator, but nothing to do with virtual spacing address. What the fuck? Give me a free 4 KB block of RAM. Yeah, this is what I want to do. This is exactly what I want to do because I want something. Because I want some memory. Yeah, I mean, like, I want something that's not part of my VA already. Let's say it's a 4 KB block of RAM. So I say VA to PA. Physical pages. What the fuck do you mean? If I'm gonna make a page table entry means it's pointing to some physical address. Is it not? What is a page table entry? Page table entry is just an entry in a table, and that table is used by MMU. So whenever I try to send a virtual address, it's going to look up in that table, and if that address is present in the table, it will be a valid memory. If it were to be in that table, that means that VA has a physical address. What the fuck do you mean by this? There are two paths. There are no two paths. Mm. Can I pause my... I'm getting call. Fuck. It's fine. I guess I'll just... Da, 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 da. Is there a mute at least? Okay, fine, whatever. What's the difference between allocating a page and mapping a page? There's no fucking difference. I'm going to say there is no fucking difference. There's no fucking difference, you piece of shit. How come a page table entry means you are providing a VA to PA? So there's already a PA. Those fucking LLMs. A piece of shit. A page table entry must contain a physical. Yes, that's the fucking thing I'm saying. If I create a page entry, I already have a PA. Where does the physical address come from? Physical page table. And it does not magically give you a physical page. Ah, so you mean like I have to keep track of the physical pages I hold? That's not that's not even something. Yeah, I know that we need to keep track of things and make sure that that physical page is not already allocated. But yes, it's a responsibility. I know the fucking thing. I was just trying to say that in an actual metaphorical sense, getting new memory just means adding new page. That's all. And assuming that that page is free. That's a different topic from, but in my sense, in this fucking sense, we are just trying to get more memory so we get an extra page, we get extra space. That's it. Yeah, I get this point. So that you don't have someone else who also try to get the same fucking page. Okay. So there's two things that needs to be done. We need to keep track of our memory, and then we can allocate pages. Okay, so we need an allocator that can keep track of the physical pages that we are using currently, either by kernel or by user, whatever it is. And we have the MMU map helper that will just add a new entry for a page. So let's think about designing simplest form of these two helpers. Don't write any code, any fucking code. Just explain me what the fuck have to do. Okay, so let's design the simplest physical allocator and the simplest possible mapping helper with absolute no code with conceptual recognition. Did I ask you to fucking say those stuff? Physical page allocator track. Oh, fucking track which physical page are free and which are used. Yeah, so this is going to be the allocator that's going to help us track memory, what you need, a data structure telling you free use space. simple as a bitmap, 1 bit per physical page. Okay, if RAM is 200 MB, pages are okay, so you need bits, that's 60 KB bitmap. Okay, so it's like saying you are more like a hash map, but because we have a static amount of things, we can call it a bitmap and just use the bits to directly hash into it and make sure every bit maps to a page, and we know that whether if this page has been used or not based on whether we have that key being set, key as in the bit. Okay, and we make sure the existing memory that's already being used are also being set to 1. Okay, now a function to get the free basic scan bitmap, find 0 bits, flip it to 1, return the physical page. That's it. So this is all we have to write. Interesting. Yeah, I know that, but I guess that algorithm is not that simple, because I know that memory allocators has been abused a lot, and every allocator has its own exploits. Not as in exploiting the allocator itself, it's just abusing the allocator when you have some other exploits. And it's actually interesting to see it. Okay. Okay, so I guess we can think about writing it now. uh, okay, guys. Let's think. Now we have to start fucking thinking about how to write this. We need a data structure telling you the free and used states, okay? And if the RAM is, so how do we know how much RAM do we have? Maybe currently let's keep it as static. So even if we were to keep it as static, no, we know that because that's our virtual space, because we have 42 bits. Based on that, we can consider how much of overall memory we might be using. Okay, makes sense. Okay. What's that bit name? It must be TCR EL1, but it's TCR EL1. Maybe I have to first finish up these things. No, I still don't have an user space, so it's fine. We have that will give us the VA bits. That will be the total RAM. So we can take that bits to get the total RAM. Why did I type the same fucking thing again? And divide it by 4 KB pages, and we'll get how much bitmap we may need. So we have a bitmap and we have to put it inside a structure. If we keep it inside a structure, do we get any advantage? I don't know. I don't think so. I'm not sure. Let's just see if our reasoning is reasonable. Okay. Why the fuck? I know you fucking piece of shit. I know that VA is not the total RAM, but we use that VA to map something. So, oh, maybe it's true because we are actually trying to keep track of the physical memory, not the virtual memory. Okay, so we need to keep track of the physical memory. Virtual memory, anyone can allocate anything. Okay. I'm the fucking piece of shit here. I agree with you. Oh, fine. Okay, so. Oh, okay. So we are keeping track of the physical RAM. So first of all, how do we get the total RAM that we have? Maybe I have missed that information. That's true. Virtual space is for anyone. Kernel, yeah, definitely kernel has identity map, but user space can in different processes, and they are all going to be mapped to a virtual. There's no CPU. Read the DDB address x0 in stars, parse the DDB header and nodes, find the node memory. Okay. I get it. So this is something that I've been trying out because when I tried to build this fucking thing previously, I used this address 4000, I guess, and I got an error saying that that fucking address has been previously used by someone else, and it's called DTB. What the fuck? And I had to fucking change it to 8000 because that's QUMU's what's that natural way to say that. I would say hard-coded address. Okay. Oh, that's fine. Let's just say. Okay, let's write it. Okay. Let's. Don't fucking write any code. Just give me the structure of DTB in memory layout in ASCII art, so I can write it. I don't have to fucking add some extra shit. It's not gonna make any difference. Huh, interesting. This is how it's gonna look. Let's see if we can find this magic bits first of all. Let's fucking run our code. We have the fucking GDB. And we are in the start. Now let's disassemble 0x04 1 2 3 1 2 3 4. What should I put? Star? I don't fucking know. Maybe I'll just put /xi. Oh, okay, I can inspect it this way. I'll put 10 addresses. I'll put 100 addresses. So there is something there, but I don't see this fucking magic bit. Maybe its layout is a bit different. Ah, shit. I think it is here. FED, and it's just because the Indian is How do I change the Indianness? How to change in okay, we can set show Indian. Target Indianness is set show set Indian big. Okay, let's see. We got it. So it is true. It has a proper magic number. Interesting. I think, but it uses what's that? AMD and whatever uses. But I am using ARM, so I think Big Indian is better because here everything is big. Indian. Okay. Now we need to read this bit. Assuming they all have proper structure. From the magic bits, that is 0x d e e d f e d. How to pass down to can we compute it basically total bytes of all in between or is there best way? Let's see. Well, at least we have one thing working. So I believe it must be somewhere in this or somewhere in this. Use the offsets stored in the header. Okay. So for every header, they already give the offsets. Oh, CV. So this is the total size. DDB base plus off TTD structs. This fucking parsing is going to fucking kill. We just should assume that we have 4 GB RAM. That would be far simple. Write a C helper for this. Fucking fuck. Or we can write it. I think it's not that hard. If we can take this, well, let's try. There's nothing wrong in trying. dtd dot c. If standard int does not have it, then you fucking don't want it. You int 32. 32 underscore t. Do we have that? I think we do have that. Okay. Let's parse void int. No. What exactly am I gonna return? I don't know. What am I gonna return? What am I gonna return? Let's just say we're gonna return an address. Then it should be uint 64. Get total RAM. And let's fucking define what's that? DTD base. Let's say 0x 4 1 2 3 1 2 3 4. Okay, we have a base. Maybe we have to put attribute something to make it align. Let's just split view. What's that split view? Huh. Interesting. How to make a struct bytes aligned without any extra padding in C, so we don't get any fucking padded bullshit. Packed. It's fucking packed. It's fucking packed. Attribute packed. I think we can add attribute here too. Attribute. Packed. Okay, this should work. This should work. Put type diff. Now I'm trying to understand how can I map DTT struct from this place. I think we just have to put something like DTD pointer. Header equal to GTD base. Would that work? Or do we have to do something like DTD star here? And then if I put header, can get magic bytes. Let's just see it. Let's see how it will turn out. Test. Hopefully this won't get what is that, removed by our optimizers, compiler optimizers. And we can put extend once we have jumped every damn thing. Maybe we don't even have to jump anything, we'll just check it here directly, because we don't want MMU to fuck with us. Now let's just run it. What the fuck? Let's just pick QMU. I don't know how this piece of shit sometimes just... What? Okay, I need to compile the fucking thing. Oh, my bad, my fucking bad. My fucking bad. DTD.c DTD.o. What was that? Well, we did cut some error. We can jump. What the fuck? Interesting. What the fuck did I do wrong? Let's just see. What? we have a address. We are saying that it's a DTD pointer. Oh, it's not a DTD pointer. It is DTD. Okay. Okay. I get it. Struct. Now I'm being fucking confused. I don't even know pointers properly. What? What pact? What's a pointer? Pointer is just variable that has an address. No, that has a address to something else. And a struct is also just an address. I think I did it correctly in the first turn, because if I cast this, then I'm saying that this is a DTD pointer. And why is packed not working? Do I have to put it in the end? What does that even mean? Oh, okay, I have to put it after struct. Okay, let's see. Something is fucking wrong. That's why we need to know the basics first of all. Without knowing the basics, we can't do any damn fucking thing. Let's put SP here. SP is pointing to some. Okay. Okay. I understand. My fucking stack pointer itself is not even initialized. Why the fuck am I trying to do random things? I can put it here. Now we'll get some better errors. We'll still get errors, but at least we'll get better errors. Okay. So it did work. So I was not that much of a fool. let's run it again. We put something there and take some pointer into x8. I believe that should be the address. Let's examine that. So currently it's x0. So it's correct. So did they put it on top of the stack? Let's check after loading. Maybe it's in top of the stack. SP. And 10 SP. We have the address and stack. This address plus 12. Oh, I'm fucking shitting it. I'm doing something wrong. Okay, let's fucking... it is correct because I am taking the magic number. That's why this value is in 8. It is correct. Let's see. There is no return value. Let's just return test then. Well, we are returning U32 in U64, but that doesn't matter. Let's just see if my fucking code actually worked. Yes, we have it here. Now let's just take header dot we want what do we want? I fucking forgot. DTB base plus offset instruct. Okay, let's see. I think we are correct. I don't know. What? Why is 4000 there? That's DTB base. Well, let's just fucking ask it. Bring it. Correct. DDB fields must be byte swapped. Okay. In ARM, it will be in Big Indian. Okay. That's why initially it looked different in our thing. Okay, yeah. Yeah, that's why we see it like this. Okay. I didn't say it will return. I'm just trying to check if it is working. We check the magic number. Okay. They have to use built-in swap, whatever. Okay. Let's try to use that. DD struct. Okay. Now we can walk. Now we need to walk the nodes. Walk the nodes. Read the tokens in a loop. Give me the struct layout. Dude, I asked for the structure layout of this. We need to pass those tokens and explain more about how the token structure will memory and how we can think about parsing it. But if we can have a struct, we can point to it and do the parsing even faster, right? Okay, the structure block is not a C struct, it's a flat stream of tokens. Okay. No predictable structure layout. Okay, fuck. So there is no predictable structure layout. Okay. Read 4 tokens. Switch based on the token. Is all tokens are of same size? We are doing it recursively because nodes can have internal nodes. I'm thinking whether do we need to write this whole fucking thing? Well, we have already started, so there's no point in stopping. Mm. So we have the struct and current node will be null and stack is equal to empty. So we need a stack. I am in low level code. I don't have a stack. I don't have a stack, but I can push it to the actual stack. First in, first out, right? Maybe I can keep a linked list or just add it to head. Yeah, because we don't care about other things, so we can just hard code whether we have reached memory and just go on with it. I guess that's a good thing. We can try to do that. We have to read. Now only missing part is this. How to implement implement this. Then we have the algorithm. I guess we just need to read 4 bytes. We are reading 32-bit. We are swapping. I guess we can use this method. Pushing 0th bit to 24th bit, first bit to a 16th bit, second to 8th bit. But second would be already at 16th bit. How would I left shift it and bring it to here? No. Because I'm indexing it, we would have already gotten just the value. We just have to push it to whichever place we want it to push. We want it to be pushed. Interesting. But we'll put static inline read 32 B32. This is our logic. Uint 32 star pointer. We have a uint 32 pointer. No. Let's just say it's we have to swap the bytes, so we can say it as uint 8-bit p equal to star 8-bit star of pointer. Then we can index into it. The return a final value. That value has 4 things. The first thing is U32. No, it's U32. And we have PF0. PF0 is U32, but no. We finally change it into that. We left shift this to 24th bit, and then we are I think we left shift the first one to 16th bit. We left shift the second index to 8th bit. We don't do anything about the last one. We can just shift it to 0. If we add all these things, we would have swapped the entire thing. I hope so. I don't know. Let's write a for loop. And 16. Index equals 0. Index. We don't have an end case, which is always index plus plus. No. I'm not supposed to index this here. Index will also be updated internally. This will be an interesting for loop. I could have just put while, but whatever. And then I can just say I need to read the first p value, first token value, uint32 bit token equal to read v32 of dt struct. Now the thing is, this is u32, so we can say that it's a pointer to 8-bit values. I don't know. And then we upgrade index by 4. write a switch case, and expression is token. No. We have to. We just read the starting value, and it's address. We need to. Guys, I'm fucking.